last unit we studied kinematics. We defined that at the very beginning of the unit as the study of motion. And of course, you know after the unit's over, that's what we focused on for the entire unit, right? Motion. The study of motion without regard to what causes that motion. If you think back, okay, we looked at one-dimensional motion, collinear motion, looked at two-dimensional motion or non-collinear motion, but not once did we talk about why that motion was happening. Not once did we talk about how that motion was happening. That's kinematics, the study of motion without paying any attention to what causes the motion. That's as opposed to dynamics, which we're going to study in this unit, which is the study of motion. But this time, we're going to pay attention to, in fact, we're going to focus on what causes that motion. So we'll say, with regard to what causes the motion. Can anybody tell me what causes motion? Margaret? Forces, yes. So in other words, we're going to study forces in this unit. We can call the unit dynamics, or we could call the unit forces, because that's what we're really going to study here. Now, that doesn't mean all the stuff that we've done in Unit 1 is gone out the window now. We'll still use that stuff, because we're still studying motion, and that describes motion. Now we're just going to get a little deeper into it and describe exactly what's causing the motion and how it's happening. In other words, we're going to study the forces in addition to what we've already done. Who can tell me what a force is? I know you've learned this at least as far back as grade 6, when you were studying, did a flight unit in grade 6, and you talked about a number of different forces, including a lift force, a drag force. You can tell me what a force is. It's a simple 4-word definition. Push or pull. I guess that's 5 words. Having a little trouble counting this morning. Okay, it's a 5-word definition. It's a push or a pull. You guys all knew that, right? Okay, we'll make it 4 words, yes. It's a push or a pull. Now, that push or pull can come from me. I can do the pushing. Okay, right now, pushing Lane's desk or pulling Lane's desk. That's a force. But it can also come from, let's say there was an earthquake right now and Lane's desk started moving, and that force, that push or the pull could come from something else, like the earthquake as well. Or if something hit it, something ran into it, okay, then that could apply the force as well, the push or the pull. Now, there's 2 things that a push or pull can do, that a force can do. Those 2 things are, number 1, let's see if you can tell me actually. Okay, let's see if you can think about it. You've probably never heard this before, but let's see if you can logically come up with an answer here. There's 2 things that a force can do. What do you think one of them is? Yeah? Okay, get an object to start moving or stop moving. Okay, I'm not going to write that down quite yet, Riker, but you're absolutely right. You can get an object to start moving or stop moving. Right now, the desk isn't moving. If I want to get it to move, I can apply a force. I can push it or I can pull it, and that will cause the desk to start moving. Or if the desk was already moving, or let's say a curling rock was sliding down the ice, I can apply a force to stop that object. Sometimes when I apply a force on that curling rock, though, it doesn't stop the object, it just slows it down. Sometimes if I apply a force on a curling rock, it doesn't get it started. Maybe it's already moving. I just get it going faster. So not only can I start or stop an object with a force, I can get it moving faster or slower, speed it up or slow it down with a force. What do you call that? When an object is starting or stopping or speeding up or slowing down, what's the one word that describes all of those? What's the one A word that describes all of those? Wayne? Acceleration. A force can cause acceleration. Now, there's one other thing that an acceleration can do besides start an object, stop an object, speed up an object, slow down an object. Acceleration is the rate of change of velocity. Velocity is a vector, direction included with that. You can actually have an acceleration even when the speed of the object isn't changing, when it's not speeding up or slowing down. When can you have an acceleration? How can you have an acceleration if the object isn't speeding up or slowing down? What can happen there, Travis? No. Yeah. When you're changing direction. Yeah, since velocity is a vector, if you're changing velocity, okay, then you can change it either by changing its speed or by changing its direction. And if you're changing velocity, you have an acceleration. So a force can cause acceleration. It can cause it to speed up. It can cause it to slow down. It can cause it to start. It can cause it to stop. Or it can cause it to change direction. All of those things fit within, can't spell direction. I need some direction on how to spell direction. There we go. Cause it to speed up, slow down, stop, start, or change direction. All those things fit within a force causing an acceleration. Now, what else can a force do besides cause an object to speed up or slow down or change direction or start or stop? Take a look up here. What do I got in my hand right now? What do I have in my hand right now? Water bottle. Okay, let me do this. Let me squeeze this. Am I causing this water bottle to speed up or slow down or change direction? Bo? What am I doing? I'm changing the shape. So a force can change the shape of an object, or as Riker said up here, can deform an object. Okay, I don't care what word you use, change shape, deform object, whatever, it all means the same thing. You push on something, let's say you push on a car, and you're having trouble moving that car. Okay, that car's staying at rest. You're not accelerating that object. What are you doing to that car? Are you deforming it? Changing the shape of that car? Well, yes, you are, actually. Yes, you are. Very, very little. So little that you probably aren't even going to notice that you're changing the shape of it. But you are changing the shape of it. Now, in all likelihood, that shape is just going to go right back. It's going to bounce back to where it started, so that in the end, there's not going to be a net change of shape. But as you're pushing it, if you're not accelerating it, you're changing the shape. All right. What's a net force? What's the word net mean? Net, not in the context of, jumping off a ledge and being caught in a net and stopping you. What does the word net mean normally? Yeah, it's a total. Okay, I get a pay stub at the end of the month, and those of you who have jobs will also get a pay stub at the end of the month listing everything, right? How much money you get deposited into your bank account, and how much money was taken off for taxes, and how much money was taken off for employment insurance, and how much money was taken off for me for pension and for benefits and all that stuff. Okay? At the top of the pay stub, it has your gross salary. Okay, that's the amount of money that you get, the amount of money that you get paid. Let's say you get $10 an hour, you work 10 hours, it's $100. Your gross salary would be $100 there. Okay, your net salary, which is the number at the bottom, is usually, at least as you get older, significantly less than your gross salary. It's the total. It's the total once we add up all the things that were added into there, including the things that were negative, like pension and employment insurance. I missed the other day because I was at cross-country meet at Strathcona Tweedsmuir. Okay, when I get my pay stub this month, it'll list my gross salary. Okay, at the top of the page, which is the same every single month, my gross salary, and then it's going to add to that. It's going to add to that a day for. No, sorry, it won't do that for missing a day for cross country. If I was sick, okay, then it would add to that some sick pay. Okay, so we'd add some sick pay to that, but then it would take away some sub pay, so that in the end it ends up being the same thing. But then it would take away from that or add a negative value of that for taxes, for employment insurance, for Canada pension, for benefits, and whatever, so that in the end, you end up with barely more than half of what you started with. The net pay at the bottom, is the total after I've added everything together. Now, I don't know, for me, I've always thought it should be the other way around, because I look at this top number here. I really like that top number. It's a good number. Okay, the bottom number, the net pay, which is actually what I actually get, okay, that's the number that I don't like so much, because it's half gone, or almost half gone. I always thought that this one should be called the gross pay, and this one should be called the net pay, because I like this. Okay, this one is the one that's gross, because half my money is gone before I ever see it. But in the end, that's not what it is. Gross is what you start with. Net is at the end, after you've added everything together. The net force is the total force after you've added all of the forces together. If you have a force to the right of 10 newtons, a force to the right of 5 newtons, the net force is 15. If you have a force to the right of 10 and a force to the left of 5, then the net force is 5. Now let's define a couple more terms. Inertia. You know where everybody knows, I know where everybody knows this term from. Everybody's heard this term before, and everybody's thinking the exact same thing right now. Everybody's thinking of the Bill Nye video, at the very beginning in the intro where it says, inertia is a property of, right? Everybody's thinking of that? Except people that don't know who Bill Nye is, because they grew up in a...
No.
England. Yes. Inertia is a property of matter, so what is it?
Would it be a property of an object that is in motion?
Gentlemen? I'm sorry?
A property of an object that is in motion, stay in motion?
Kind of. Rutger said the property of motion that kind of keeps an object to stay in motion, or something. You said something like that, right, Rutger? Yeah. You're kind of right. The tendency of an object to stay in motion, you're still kind of right, but not completely. Inertia is the tendency of an object to resist a change in motion. The tendency to resist a change in motion. So Rutger said, basically, it's a tendency to stay in motion. All right? An object has a tendency, if it's already in motion, it has a tendency to stay in motion. And that's inertia, right? It has a tendency to resist a change. It's moving, doesn't want to change, wants to stay in motion. Okay, that's inertia. But, Rutger, right now your desk is at rest, right? Your desk is at rest. That desk wants to keep its current state of motion as well, which is at rest. So that desk also has inertia. In fact, that desk has just as much inertia as it sits there at rest as if it was on the back of a semi-truck going down the highway at 100 kilometers per hour. Because that desk has a tendency to resist a change in motion right now as it sits there, just as much as it has a tendency to resist a change in motion when it's going down the highway on the back of a truck at 100 kilometers per hour. Inertia is a tendency to keep doing what it's doing, whether it's at rest, whether it's moving at 4 kilometers per hour, or whether it's moving at 100 kilometers per hour. It wants to keep doing what it's doing. Now, what factor is responsible for inertia? What factor, what property of that desk, or whatever it is that we're talking about here, wants to keep, or is necessary to keep an object doing what it's doing? Yes. Inertia is not mass, but it comes from mass. The heavier an object is, the more inertia it has. The heavier an object is, the more it wants to resist a change in motion. You got a go-kart out in the parking lot. You have the delivery truck out in the parking lot. You give each of them a push. Okay, you push as hard as you can on both of them. They will both have a tendency to resist a change in motion. The go-kart wants to stay at rest. The semi-truck wants to stay at rest as well. Which one wants to stay at rest more? Which one is harder to get moving? The semi-truck is, right? Why? Because it's heavier. The more mass something has, the more inertia something has. You got a semi-truck traveling down the road at 100 kilometers per hour. You got a smart car traveling down the road at 100 kilometers per hour. They both want to keep going at 100. Neither one of them want to slow down or speed up. But one of them has more inertia than the other. One of them has a harder time stopping than the other one does. Which one has a harder time stopping? The truck, right? The truck. Why? Because it's heavier. The more inertia, or the more mass, I should say, the more inertia something has. Two more terms. Static equilibrium. What does the word static mean? Static means what? No change, okay? At rest, okay, not moving. Static equilibrium, let's talk about the other term before we put them together. Equilibrium. Chemistry people might be able to kind of give me a decent definition for that. Chemistry is useful for something, right? What's the word equilibrium mean? Okay, equaling out, balancing, sure. Yeah, both of those are a good way to put it. So if you've got static equilibrium, you've got something that's at rest with balanced forces. We'll say object at rest with balanced forces. What happens? What happens if you have an object at rest with balanced forces? What happens to that object? Okay, right now, Olivia's desk is at rest. Okay, I'm going to push on Olivia's desk right now. Okay, it's not moving. There must be friction acting the other way. So I'm pushing to the right. Friction is pushing to the left. The desk isn't moving. What happens when that object is at rest and the forces of friction and my applied force balance each other? What happens to the desk? Pardon me? Somebody said it? It's going to stay there. It's in static equilibrium. It's not going to move. The forces are balanced. It's going to stay where it is. Now, that's as opposed to translational equilibrium. That's moving equilibrium. We'll say a moving object with balanced forces. What's going to happen to that object? You get a car traveling down the road at 80 kilometers per hour. And there's a force acting on it forward caused by the engine of the car. There's a force acting on it backward caused by air resistance and by friction. Those forces balance. What happens to the car? It keeps doing what it's doing. It will keep going at the same speed of 80 kilometers per hour in a straight line. Okay? Inertia, the tendency of an object to keep doing what it's doing, to resist a change in motion. If it's at rest and the forces are balanced, it's going to stay at rest. If it's moving and the forces are balanced, it's going to stay moving at the same speed in a straight line until one of the forces aren't balanced anymore. The only way you get a car to stop is if you upset that translational equilibrium. If you take one of the forces and make it not balanced. If one of the forces is bigger than the other ones, that's when it stops. So static equilibrium, object at rest with balanced forces, stays at rest. Translational equilibrium, moving object with balanced forces, stays moving. We'll say at a constant velocity in a straight line. In other words, whatever it's doing, it wants to keep doing. If it's at rest, it wants to stay there. If it's moving, it wants to stay there. This all leads to something that we call Newton's first law, which you've probably heard before. Newton's first law is sometimes called the law of inertia. The law of inertia, or Newton's first law, has two aspects to it. The first aspect says an object at rest will stay at rest An object at rest will stay at rest until there's an unbalanced force, until there's a net force. Notice I didn't say an object at rest stays at rest until a force acts on it. We can have 50 forces acting on an object at rest. It can still stay at rest, as long as those forces balance. Right now, Olivia's desk, if you look at it, you think there's no forces acting on that desk right now? There's lots of forces acting on that desk. Gravity, there's something that we call the normal force, which we'll talk about later on. There's some friction probably if there's any kind of movement, any kind of pushing to the side. Maybe there's some kind of breeze that's pushing on the desk, or all kinds of forces acting on it. We're not saying that there's no forces. There's lots of forces, but the forces are balanced. Okay, as long as they're balanced, the object is going to stay at rest. Now, an object in motion will stay in motion. It's going to stay in motion in a straight line. At a constant velocity until acted upon by an unbalanced force. I remember years ago when the first stoplight going in on McLeod Trail to Calgary was at, I think it's 162nd there in Sun Valley Boulevard. When you get to Shaughnessy, right? When you go to turn left and you go to Walmart and the movie theater in that area in Shaughnessy. That was the first stoplight. Now it's the second one. Pretty soon it's going to be the third one as you're going into Calgary. And I remember years ago stopping at that stop sign, stopping at that stoplight that was there. Okay, it's a red light. Okay, I see it long enough in advance. I slow down. Okay, I slow down, I slow down, I slow down. I stop. There's a person in front of me. Okay, he's stopped. I'm stopped. There's a person behind me driving up. She slows down, slows down, slows down. She slows down. She stops right behind me. It's all good. And then all of a sudden, the light's still red. She just decided to go. So she puts her foot on the accelerator and she goes and she runs into the back of me. Okay, now, nobody was hurt. I wasn't injured. She wasn't hurt. In the end, nobody was hurt because she wasn't moving very fast when she hit me. Right? If she had just been going at 80 kilometers per hour and hit me when I was at rest, then I probably would have gotten whiplash. But because I was already stopped and she had just started moving, I have no idea why she did that. She stopped at the stoplight, and then she just went before this light turned green. You guys know intuitively, though, in a case like that, you can get whiplash. What happens? What is a whiplash? Where does it come from? Well, you're sitting in your car, just like I am right now in this seat. Okay, you're sitting at rest. Somebody hits you from behind. What happens? Your head goes back, right? Your head gets pushed back, and that can stretch the muscles in your neck, and that gives you whiplash. That's what whiplash is, right? Is stretching of the muscles in the neck. Is that what happens? Not at all. Not at all. Why would your head go back?
Because your body's pushed forward by the seat.
Your head does not go back. There's no reason for your head to go back. Okay, you're sitting here at this stoplight. You get hit from behind. There's no reason for your head to go back. Okay, you're hit from behind. What happens? Your body, which was at rest and wants to stay at rest forever until acted upon by an unbalanced force, now experiences an unbalanced force. That's the force of the car behind you pushing on you. So now there's a force on my body. What happens to my body? Well, my body doesn't stay at rest anymore. So my body goes forward. What happens to my head? It doesn't go back. My head just stays at rest. So my body goes forward, my head stays at rest, and the effect of that is like your head is pushed backwards, but it's not. Okay, you feel like your head is pushed backwards, but it's not. It's your body being pushed forwards. Any way you look at it, you're going to stretch your neck muscles and get whiplash, but it's not really being pushed backwards. Does that make sense? Your head wants to remain at rest, and it does remain at rest until your neck muscles finally pull it forward. That's, by the way, why having the headrest up, the headrest in the seat of the car is supposed to be not where your neck is. It's supposed to be behind the ball of your head, the back of your head. That's so that there is a net force acting on your head. If you get hit from behind, your head doesn't stay where it is. Your head gets pushed forward by the back of the seat. Okay, if you don't have that, then that's when you get whiplash. Okay. I want to do a little demonstration here. I can get somebody in the front just to switch seats for a few minutes here. Right there, maybe if you don't mind, just go back here behind Maddie. All right, what you see right here now is a placemat with a plastic fork and a plastic knife on it, and you see a coffee cup, and it's got some water in the bottom of the coffee cup. And you guys saw me pour it in there, so you know that there's water in there, right? Obviously, the fork and the knife are fairly light because they're plastic forks and knives, although they're the good ones. Okay, no cheaping out on plastic forks for me. It's always the good ones. Still light though. This is pretty heavy because it's a pretty big mug to begin with, and then there's some water at the bottom of it. Okay, I want you to watch what I'm going to do right now. Okay. I'm going to demonstrate Newton's first law, the law of inertia, which says, in part at least, an object at rest wants to remain at rest or will remain at rest forever until acted upon by an unbalanced force. Okay, so this cup is at rest. It wants to stay there. The knife and the fork are at rest. It wants to stay there unless I apply an unbalanced force. Now, if I take each of the corners of this placemat and I give it a quick tug, then I should be able to keep these objects at rest because I'm applying only a very, very tiny force on the cup and on the fork and on the knife. Not so worried about the fork and the knife here because they're plastic, and a little bit more worried about the cup with it's breakable with the water that's inside. But hey, physics says it should stay where it is, right? When I give it a tug, if I do it quick enough, physics says I should be able to overcome friction and apply only a tiniest little bit of force and keep him at rest. So on the count of 3, I'm going to give it a tug, and we'll see what happens here, okay? Count of 3. 1, 2, wait a second, I'm going to sit down for this, okay? I'm going to sit down. Let's try this again. On the count of 3, we're going to pull this placemat out from this cup that's filled with water and this plastic fork and this plastic knife. Watch closely. Okay, on the count of 3. 1, 2. Who thinks I'm going to break the cup? Who thinks the fork and the knife are going to go flying? Okay, on the count of 3, let's see. On the count of 3, let's see. Okay, 1, 2. Hands again. Who was that? Who thought they were going to? Okay. Count of 3. 1, 2, 3. You saw the cup move the tiniest little bit. The fork and the knife still stayed more or less where they were before, but they moved a little bit more than the cup did, right? Why? First of all, why did the cup pretty much stay where it was? Why did the fork and knife more or less stay where they did, but they moved a little bit more than the cup did? They all want to stay at rest, right, Turk? Go ahead. Yes, yes. Which one has more inertia, this fork or this cup? The cup does, because it's heavier, right? So which one, they all want to stay at rest, right? But which one wants to stay at rest more? The cup does, because it's heavier. It's the semi-truck versus the smart car, okay, versus the wagon. The heavier object has more inertia. It wants to keep doing what it's doing. It wants to stay at rest more. Let's try it one more time here. Years ago I did this, I remember, for a Physics 20 class. It all worked well, except I made the mistake of filling the cup up right to the brim. So a little bit of water spilled. It was all good. It worked. But a little bit of water spilled on my paper placemat here. So then my next class was at the time a grade 9 class comes in. I said, Mr. Dickie, what were you doing? Like what were you doing? I said, well, I explained it to them. I said, in my Physics 20 class, we're talking about inertia. And I said, how these objects want to stay at rest. And they said, well, can you do it for us? So I said, sure. So we tried it with them. And then, of course, because I had spilled some of the water, I spilled some of the water on the paper, the cup stuck to the paper. It was a cup. I actually used a cup, okay, a ceramic cup, and I used a plate. I used the whole shebang here. Then I go and pull it, and everything stuck to the paper. And as I pulled it, it all just flew everywhere. It smashed into a million pieces on the floor. We're going to try to avoid that now. Now I'm careful to not fill the water very high here. Okay, on the count of 3. 1, 2, 3. Oops, I missed the one corner. So it did move a little bit more. But again, you still saw that I think that the fork moved more because the fork is lighter. Okay, objects at rest want to stay at rest. The heavier it is, the more they want to stay at rest because they have even more inertia. Object in motion wants to stay in motion in a straight line at a constant velocity until acted upon by an unbalanced force. Hey, the only car accident I've ever been in when I've been driving, that is, not the only one I've ever been in, but the only one I've ever been in when I'm driving, happened when I was 16. Well, that's actually, both of them that I was in happened when I was 16. Neither of them, well, both of them were kind of my fault, I guess. First one was literally, I was 16 years old, I got my learner's permit that day. But when I was younger, you didn't get your learner's permit the day you wrote the test. They would mail it to you. So you'd write the test, then your learner's permit would get mailed to you. It arrived in the mail. My mom came after school and said, hey, your learner's permit's here. Do you want to drive home? So I drove home. And then that evening, she said, I have to go down to this person's house. You want to drive me there? So I said, sure. So we got in the car, my parents' 6-month-old car, and we started driving there. It was kind of dusk, and all of a sudden I see on the other side of the road, on the shoulder of the road on the other side, about 6 deer. So I slowed down, and then one of them all of a sudden, it's like he looked at me and knew I was a brand new driver. He just looked at me, and then he raced right, like he just ran right at me. I swear he ran right at me. Anyways, I had my learner's permit for 3 hours before I hit a deer, literally. The second and final accident that I was in, when I was 16, I used to drive, after I got my license, I drove a dry cleaning delivery van for a while. And I remember this one day was a snowy, icy day, and I'm coming, here's the highway, and here's the off-ramp to the highway that kind of comes around to the road like this, right, underneath the highway. Okay. So here's me going on the highway, and I have to turn off right here. It's a snowy, icy day. What happens? I'm going a little bit too fast right here. What happens? And I hit the guardrail right there. So why did that happen? Why did that happen? Because I was driving, I was moving. My delivery van wanted to stay at a constant speed in a straight line. Now, it wasn't initially. I was turning because there was an unbalanced force. Okay, when the forces are balanced, you go in a straight line. Here, there was an unbalanced force. What happened right here? Hit a patch of ice. When you hit a patch of ice, no longer are the forces unbalanced. Now they're balanced. There's no friction anymore. The forces are balanced, so what do? I go off in a straight line at a constant speed until acted upon by an unbalanced force, which could be anything. For me that day, it was the guardrail sitting right there. An object at rest wants to stay at rest until acted upon by an unbalanced force. An object in motion wants to stay in motion in a straight line at a constant velocity until acted upon by an unbalanced force. In end of November, beginning of December, we're going to make a trip to Edmonton. This class is to go to West Edmonton Mall, and we'll study the physics of amusement park rides. It'll be a good day. It'll be a fun day. We'll ride the roller coasters all day while everybody else is back in school working. We'll have to do some work too, but it's a fun day. Riding roller coasters is a pretty safe thing to do. Having said that, the roller coaster that we'll ride in Edmonton is actually one of the few roller coasters in the world that have actually derailed and killed people. The roller coaster that we'll ride killed, I think it was 3 people back in the 1980s. Here's what happened. Here's what happened. The roller coaster train is only 3 cars long now. It used to be 6 cars long. Okay? As it was going around a turn like this, it was too long. The car was too long and it was going too fast. The back couple cars, what do they want to do? What does every car want to do? Well, they want to keep going in a straight line, like this, right? At a constant velocity in a straight line. But because the track pulls them, applies an unbalanced force, they don't normally go off the track. There's an unbalanced force acting which causes them to turn. But those last couple of cars had enough inertia, okay, and they had so little unbalanced force that they just kept going in a straight line. They kept doing what they naturally want to do. So the back 3 cars, I think it was, just kept going in a straight line. And unfortunately, there happened to be a big post right there, a big concrete pillar post right there that these 3 cars hit as they went off the track. And of course, the results weren't good from that. Yep. Now, here's the way I look at this one. We're going to go up there and ride this. Don't want to scare you. This is probably the safest roller coaster in the world after something like that happens. Right? They inspect that thing every 2 hours. They actually shut it down for 20 minutes every 2 hours to inspect that roller coaster. How many other roller coasters do they inspect every 2 hours, literally? I'm sorry? Yeah, probably other ones that have gone off the track as well, sure. Right. That's what I figure it's safe now, right? Besides, there hasn't been a death on it in 30 years. Come on, it's fine. All right, everyone. We're done for the day, but I just want to assign you a little bit of homework for the weekend here. Page 142, number 1 to 4 and 6. 142, 1 to 4 and 6. That's it for the day.